Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss about the Prandtl mixing length theory for turbulent shear stress. So in our last lecture already have discussed about the shear stress for the turbulent flow. Along with the shear stress with the turbulent flow, we also have discussed about the Boseniuk's equation. And finally, we have discussed about the Reynolds expression for the turbulent shear stress. So if you remember in the last lecture, what we got in the finally, we got from the Reynolds expression what it was concluded. The shear stress, it was revised in terms of tau. This was the expression was there, tau bar equal to rho u dash v dash and whole bar. So this was the expression given by this Reynolds. Now after that, here also some constant and some limitations are there, which was identified by the Prandtl, L. Prandtl. The name of the scientist was M. Prandtl. In 1925, he given this one theory, which was modified version of this. Actually, in this equation, if you see this equation, to measure the turbulent shear stress, this is the shear stress, okay? This equation was given for to identify the shear stress in the turbulent flow, okay? So to measure the turbulent shear stress, okay, can be calculated by depending upon this C, these two values, U dash and V dash. When these values are known, this will be calculated. But the problem is here, it is difficult to measure the U dash V dash. Okay, because it is there is a fluctuation velocity is there. That's why we have taken the average of that. But there also, it is very difficult to measure the U dash and V dash. So to overcome this situation, actually, Prandtl given a theory in that mixing length hypothesis was there. That is mixing length hypothesis is there. What is that mixing length? A mixing length hypothesis is which will be used only for to express the turbulent shear stress. To express the turbulent shear stress, that is why is given so that it can be measurable. So how it can be measurable? Suppose, let's see, this is the x direction and this is y direction, suppose. In this two direction, the flows, the liquids are flowing, suppose with a velocity is there. Now these are the some length, or you can say this is the values are there. Let's start from here. The curve is like this. So it will be up to here and this will be not there. So this one you can erase this. This is how. So the velocity profiles are given like this. So this is the distance, like y height or y direction. The values are there. So the velocity here actually, suppose this is the average velocity. You can take the here. This is the value what you have taken. U(r) is the velocity at this point. So this point actually is situated from here to here with a distance of what? Maybe suppose y1 distance is there from here to here, from this base point. Okay. Now, if this is the U bar is there, then to identify the velocity of the surrounding zones or this different layers of this near to this layer. So what is that? Now from here to here, we need to give the L. This is L and this is also L. So all will be same height length you need to consider. So here also L, here also L. Now if I'll go for this one, if I measure this one, then what I can do now, U1 U bar minus L, I can go for it, and this one I can go for it U bar plus L. So there is a height is there here. So this is the fixed surface. What is there? When the liquid is flowing in over the surface, for that condition we have taken this. Okay. So if you have seen the previous, you can understand more. And here is the free stream velocity, suppose is there. Okay. Now, so this according to this Prandtl theory, this mixing length, that will be, what is this? L will be, this is the distance between the two layers. Distance between two layers. Now see, this is one layer, this is one layer. So L we can write, this is the distance between two layers. Okay, which are in the transverse direction. Okay, and you can say next, like nearby, what are the layers are there? For that, we need to consider this is also L, here also L we can consider. Now, so that the momentum which will be created, or the particles which are mixed at this zone, you can say at this layer, okay, that momentum of the particles in the direction of S, in the direction of X, in this direction, okay, it will be same. That means the momentum what is created here and the momentum what is created here at this zone, that all will be considered the same. That means what will the momentum of this? The momentum, we know that mass into velocity. So velocity what we have taken, now u bar, okay, average velocity. So at this zone, at this surroundings, at this area, what are the velocities are there, that will be identified, and along with the mass of the object. So the momentum of this fluid, of this particle in the x direction will be same. So there will be no problem in that. So that what he assumed, okay, so the velocity fluctuation what we have discussed in the previous time, velocity fluctuation in the sense, as I told you, suppose this is the x direction, again this is y direction. So velocity fluctuation means you can get a curve like this. You can get a curve like this in up and down. Okay, so now suppose this is for laminar flow, this is the laminar flow, this is for turbulent flow, this is for laminar flow, this is for turbulent. So here you can get some fluctuations of velocity. So now what he assumed that the velocity fluctuation in the x direction, what is there in the x direction, that is u dash, okay, that is u dash. Now it is related to this length. Which length? With the mixing length. Okay, so this u dash was taken in terms of this length L. So that what we have given this equation, now u dash equal to L into du by dy. So du by dy is nothing but, what is that? The velocity gradient in this zone. Okay, so L into the length what is there, and du by dy. So this was one equation he given in the direction of x, only x direction. Similarly, y direction also there. Now for the y direction also, the velocity component in the y direction also same as the x direction. So that also we need to consider. See, we can consider that this is only y direction, y you have taken for the x direction. For the x direction also, the length what was given, that also need to be considered. Okay, so that's why the velocity components, the fluctuation velocity equal to L into du by dy. So this one we can give equation 2. Now, in the previously, if you have seen, here we have the average of this one, like, you know, u dash v dash bar was there. So this one we can write u dash v dash bar equal to this value, we can write L du by dy into L du by dy. That means the 2 times of this double is there. So that is L square, and what we will get here, du by dy whole square. Okay, now this value what we got here, just put in the equation of this. Okay, see, already this equation was given by the Reynolds. So this expression is going to be modified by the Prandtl mixing length theory. So again what we'll get, we'll just put the value in the equation, this Reynolds expression, to get the shear stress in the turbulent flow, and that to be due to Prandtl theory. So what we can write, this is tau bar equal to, already is there, so you can write rho L square du by dy square. Okay, now this is equation 3, we can mark it. Now, so the total shear stress you can see at any point, okay, in the turbulent flow, what is that? Total shear stress of a fluid at any point in the turbulent flow. What is the sum of shear stress due to the viscous shear and turbulent shear. That again you need to be identified. This is only one. So again we need to consider this is for the shear stress for the turbulent flow. Now what about the shear stress for the laminar flow? Now already we have discussed that one. Laminar flow shear stress is nothing but the Newton's law of viscosity. Okay, so that one we know that tau equal to mu into du by dy. This is the theory given by the you can write equation 4 by the Newton's law of viscosity. So this is used for the laminar flow. This is for the turbulent flow. Now what about the total? Very simple. Just you add these two things. So finally, if you add these two things, we can write tau bar equal to this is the laminar flow. What we got, mu du by dy, and this rho L square du by dy whole square. So this is equation 4. Now this is the Prandtl mixing length theory for the turbulent shear stress. Now this viscous shear stress is negligible at the near to the boundary condition, we know that. So at this boundary condition, the viscous shear stress is negligible in the boundary condition. So this equation will be used for most of the turbulent fluid flow, okay, where the shear stress need to be calculated for the turbulent flow. Now see, very simple concept is, there is no change in the laminar flow. When the flow will be in turbulent, that means high velocity flow, at that point only we have some problem. For laminar flow, we can easily identify the shear stress. So the total shear stress will be for this is for turbulent flow as per the Prandtl theory. Okay, as per the Reynolds experiment, this was the expression was given. So I hope you understand this concept. If you are having any doubt regarding this, you can give a comment on the comment box. Thank you all.